All right, so we are going to go through the solution for problem number 10 of the equilibrium problem set, where we have Kang sledding down a 30-degree hill at a constant velocity. We know that Kang has a weight of 250 newtons, and we're finding the magnitude and direction of the other forces acting on Kang. So our first step for thinking about this problem is writing down the things that we know from the problem and what we're looking for. So I know that Kang has a weight, which is his force due to gravity, of 250 newtons. And then we also know that Kang is on a 30-degree hill. So I can make a little sketch of Kang on the hill and be like, oh hey, I know that the angle between the ground and the hill is 30 degrees. And I know that Kang is sledding down that hill. So I can be like, here's Kang, he's sledding down the hill. Apparently he's a little fuzzy blob. That's okay. That's just a little sketch of our problem so that we can think about what's going on. And we also know that Kang is sledding down the hill at a constant velocity. So the constant velocity part tells us that Kang is actually in equilibrium, which means that the sum of the forces is going to be equal to 0. And then the things that we're looking for are the magnitude and direction of the other forces acting on Kang. So we've thought about what we know, what we're looking for. Now I want to make a free body diagram of Kang sledding down the hill. And so I'm going to make my hill. I've made this a lot steeper than 30 degrees, but that's okay. It's just a sketch. So I add my box for Kang on my free body diagram, and I say, oh, I know that he has a force of gravity going straight down, because of the force of gravity is always straight down. I'm going to label it with a little FG. I know that Kang has a normal force holding him up, and that's the force from the hill, holding him from falling through that hill. And it's perpendicular to the hill, just like we talked about in class, so that's our normal force. And there's a frictional force acting on Kang, which is opposing his motion down the hill. So that's our force friction. Since we know the force of gravity, the forces we're looking for are the force of friction and the normal force. So we can look at our next step. We've made a sketch and a free body diagram of our situation, and we want to think about where our coordinate system should go. So in hill problems, it's infinitely helpful to make your x-y coordinates go along the hill so that I can have my x coordinate going down the hill, and then my y coordinate's going to be at a 90-degree angle to that, so it's perpendicular to the hill. That's my y coordinate. So I've got my x and y coordinates figured out where they go, and our next part is breaking our forces into x and y components. For the forces we have here, we can see that the force of friction is just in the x direction, so it's already happy, it's good to go. And the normal force is also already in one direction, it's in the y direction, so it's also set. But our force of gravity is going at a different angle in between the x and y axis. So we want to think about what that angle is. I know that down here in my corner we have 30 degrees, just like in our picture up here, which then means that because there's a 90-degree angle between gravity, so if I have a 90-degree angle right here, the other angle of the triangle must be 60 degrees, since 60 plus 90 plus 30 equals 180, and my angles of the triangle have to add up to 180. So I can say that the angle between the force of gravity and the x axis is going to be 60 degrees. So we can write that down, that's something we know. And gravity is the force that we're going to have to break into its component parts. So it needs an x component and a y component, and that just means that it has to be along the x-axis and along the y-axis. So in the x-axis, gravity goes over, and it's only going to go over as far as gravity is wide in the x-axis. And gravity goes down in the y-axis, only as far as gravity is tall. And you should note, really importantly, that gravity and that the x and y components of gravity here are at 90-degree angles to each other. They're perpendicular. They have to be perpendicular to each other. Otherwise, You're just drawing a meaningless triangle that's not telling you about the components of gravity. So I've got that 90-degree angle there. I could make a little bit of a larger sketch of my force of gravity that might help us figure out the problem. So I've got gravity here. We know that it's 250 newtons. And I have an x component and a y component. So I'm going to call this FGX, FGY. And now I can think about solving for my two components. I know the angle here is 60 degrees. So this is just like breaking down vectors into component parts like we have in class. To find FGX, we're going to take the cosine of 60 degrees, since it's a 60-degree angle, and multiply it by the hypotenuse, which is the force of gravity, so that's times 250 newtons. And if you punch that in on a calculator, you'll find that the force of gravity in the x direction is equal to 125 newtons. And you'll say, oh, hey, is it positive or negative? Well, it's going forward in the x direction, so that means that it's positive. So that's my x component. I can find my y component. That's going to be the sine of 60, since the y is opposite, times 250 newtons. And I get 216 newtons. And again, we want to think, is it positive or negative? If we're going down in the y direction, that's going to be negative, so it's a negative 216 newtons. We'll make that negative sign red so it's a little easier to see. So negative 216 newtons. We have our x and y components. Then, in our list of successful problem-solving tips, we can sum our forces and solve. And so this is the part where people sometimes get a little tripped up. But we said a little bit earlier that our net force was 0 because we were in equilibrium. So we know that our net force is 0. So I've got my net force right here. It's equal to 0. So that means that my net force in a direction, say the x direction, will also be equal to 0. So this means that if I take my forces in the x direction, which include the frictional force and that little component of gravity that's in the x direction, so plus FGX, it's going to have to add up to 0. We're looking for this frictional force, so we can take our force of gravity, which we already found for here, and plug it in and say, oh, hey, so that's 125 newtons plus the frictional force is going to be equal to 0, which means then that I can solve for my frictional force, and I get that it is equal to negative 125 newtons. And this is only telling me that it's going backwards in the x direction. So if I wanted to describe what my frictional force was equal to, I would say that my frictional force, as my final answer, is equal to 125 newtons. That's its magnitude, how big it is. And we want to describe the direction using something better, more useful than positive or negative, since that only tells us the direction on an x or y axis. So I find it really helpful to just say that it's 125 newtons up the hill, because that gives me the direction regardless of how I draw the hill. So we found our force of friction. Sweet. Then, using the same method, we can think about finding our normal force. So I say, I know that the sum of the forces in the y direction is going to be equal to, wait for it, oh, hey, 0, just like before. And the forces that we have in the y direction include that normal force that we were looking at earlier, so the Fn, and the force of gravity in the y direction. So those two forces together have to add up to 0. We already know the force of gravity in the y direction. It's negative 216 newtons plus the normal force must be equal to 0, so we can find that the normal force is equal to 216 newtons in the y direction. So then if I'm writing what my answer is for my normal force, it needs to have a magnitude and a direction, just like we had with the frictional force. So my normal force, Fn, is equal to 216 newtons. Remember those newtons, guys. I don't want to take points off for missing units, but I will. Sorry. So then we have 260 newtons, and we have to put the direction on there as well, because otherwise we're just giving a scalar. We're not telling you what the force is. We want to tell you what the force is, so 260 newtons. And if I were to describe the direction of my normal force on my picture here, I would say that it's going upwards in the y-axis, or that it's going up perpendicular to the hill. So I can go back over to my final answer here and say it's going up perpendicular to, and this little sort of upside down T is a symbol that means perpendicular, so perpendicular to the hill. So now I have my answer with both a magnitude and a direction, and we are set. Oops. So again, when you are solving these friction problems, it's really, really helpful to think about whether your forces are in equilibrium or not. Whether your forces are in equilibrium or not, and set up that XY axis in the way that is most advantageous to you. And be careful that you don't fall into that pit of despair that is drawing arbitrary triangles that we've talked about before, because you want to have those triangles be really meaningful. So I'm finding my triangle that is the X and Y components of forces that are angles, not along the X or Y axis. And going through the problem just like we did here and just like we have throughout class. Awesome. Good luck.